Looks like we can start. Welcome back, everyone. So it's been a long week. Usually the first week of the semester is pretty long, but we're nearly there. Some of you may have classes on Friday, but we're still just about there. As far as what we're doing this week, just continuing on through Unit 2A, we may finish it today, but I put in some extra time on the due date just in case it ends up getting complete on our next week. We're not going to try to race through any one of these sections, and we're only about halfway through it this one, it turns out. But aside from that, any questions or comments whatsoever to start us out today?
Hi, yeah, I have a question.
Yeah, go ahead.
For the exams that are coming up, one, two, three, and if there's any more after that, how many questions are we expecting on these?
Well, that's a great question. I think if I recall, when I did this last semester, I was going for about 10 questions. Some of the questions had multiple parts, like a part A, part B, but usually those were faster parts to make one overall question. So the total time for the exam is going to be 75 minutes. And what I'm trying to go for when I write the exam is if you're well prepared, you've gone through the homework, you did a little bit of studying to prepare yourself, you've got a good page of notes, both sides for the exam. The whole exam should take you about 50 to 60 minutes in total, getting through all 10 questions. It should all look pretty familiar. And that means for the 75-minute exam, I'm trying to bake in about 15 minutes for the typical student for just kind of checking your work, going back to make sure everything looks about right, and that kind of stuff. So about 10 questions is the number I'm going for. But the kind of the more meaningful answer is I'm not going to try to write an exam where your hand is going to write the entire 75 minutes and possibly get tired and fall asleep. It's going to be not that jam packed of an exam.
All right, thank you.
Yeah, absolutely. Thanks for asking about that. And just to add on to that, as far as the exam goes, for the upcoming exam number one and the prior exams, before we get onto week four, I'll start loading this up with more information, telling you exactly what sections we'll cover, the great review problems that you should take a look into, just extra generic information. And there's a lot of other things I have to do on my back end too, just for the sake of organization. I'll be sending a message probably Sunday evening to everyone in the class on which your preferred testing center is going to be, whether it's Pocatello Testing Center, Idaho Falls Testing Center, or many of the other remote campuses to test on. And then going from there, I'll start figuring out the procedures and everything, get everything uploaded. And before we get into week number four, I'll send everyone direct information on how to schedule your exam for your preferred testing center. So usually exam one is where we're kind of figuring out how all things will go. But after you see how it goes on exam one, exam two, it's just going to be different content, but same exact process, same idea on each of these exams. Other questions at the moment about the exams or anything else? Okay, well, we'll have a lot of extra opportunity to talk about exams. But if anything comes up, don't hesitate to ask. Either start a class after class or send me an email at any time. When we get to week four, September 14th through September 20th, what we'll be doing, this is in 3 weeks from today, we'll hold our first review on the 17th of September for our exam one. We'll also be discussing review strategies on what to put on your note card, or your page of notes rather, for the exam. So we'll be doing a good amount of preparation for getting through exam one. And again, coming to class every day, staying caught up on the homework, it shouldn't be too much of a mystery or a surprise, the problems you'll see on the real exam one. It'll be the same kind of stuff that you yourself did in my lab, that we've been doing on the lecture notes, same kind of stuff that you're going to be seeing on the quizzes starting on week two. So we'll release our very first quiz on Wednesday of week two. But I think that's pretty much all I have to say off the top of my head on exams. Any last questions or thoughts at the moment? Okay, well, let's start working towards our problem on the example six. We nearly finished that one, but we just ran out of time. And I mentioned before, we're not going to ever run past our stopping time, which is 5:40, because that's just rude. But also, I have a class at 6 o'clock. So, I mean, I'm busy too. It'd be a bad idea to run over. So, here's where we left off. I'll try to make sure we end without splitting a problem in half like we did with this one as much as possible. But this one was mainly almost done. So let's take just a look at it just for the sake of the warm up to see what we did next. We were looking into the 3-step problem solving strategy. We won't do a part A, B, and C for step 1, step 2, step 3 on every problem we solve. But for trying to figure out a problem, what it's asking, what steps to take, it's a decent strategy we'll take a look into throughout these notes. So this problem had an interesting situation where we're dealing with 25 cubic feet of water, which sounds like it's a lot. We want to know how much it's going to weigh. So the first thing to understand the problem was we told ourselves the unknown, the thing we're solving for, is the weight of the water. But when we say that, it tells us our answer has to be in pounds altogether. So step 2, solve the problem. Knowing what we were really going for, an answer in pounds, it really guides us on what the operation should be on step 2. Part B in this problem, we took the 25 cubic feet of water, and to find that weight, we used this information. 1 cubic feet weighs 62.4 pounds. So we could rewrite that as 1 cubic feet, 1 feet to power 3, divide by 62.4 pounds is 1. And you can take that whole entire equation, flip it around like this. So we had 2 equations that we could use. We're calling these conversion factors. They're both equal to 1. We did not use this one whatsoever, where the red dot is, because if we took 1 cubic feet, placed it here, we'd have cubic feet times cubic feet. So a shorter way to say why we did this operation right here is the answer is going to be in pounds. Then we took the conversion factor that has pounds already in the numerator, and that informed us, put 62.4 pounds up in the numerator, divide by 1 cubic feet. The units cancel in this nice way. That's our work on fractions working hard for us. And at the end of the day, it came out as 1,560 pounds. So really, it's a lot of work, right? A lot of people, when they look at this problem, they have great number sense. You might be one of those persons that can just look at this and say, just take 25 times 62.4. There's no reason to make kind of a mountain out of an anthill out of this. The reason we took so much time with it is eventually the problems do get trickier. It's easier to kind of lose our way and really not be sure if we're multiplying by 62.4 or dividing by 62.4. So these kind of problems are really just kind of a warm-up. They're trying to guide us before we get to units 2B, into the next chapters and so on. So we're going to take these strategies that we're developing here, even if we see the answer right away, just to show what the process looks like for when the problems get a little bit bigger, a little bit more messier to deal with. But that's what we came up with, 1,560 pounds. And part C, this is meant to be step 3 of the problem solving strategy. Explain your result. Wasn't meant to be anything too major. All we were going to say is, using the context, we can finally conclude that the weight of the water, we know it's 25 cubic feet, so we just said water for short to keep it in context, is 1,560 pounds. Or you can use the shorthand unit abbreviation LBS if you preferred. So part C, really, we didn't say anything different, right? We just stated this number. We mentioned it in context, but that's a really decent strategy all on its own, because even if you don't write that down on paper, if you just say that in your head, so this means the weight of the water is 1,560 pounds, sometimes your brain can give you a red alert if that number just doesn't make sense, if it's completely not in the right neighborhood, or in the right field you expect it to be in. The problem just sounds really silly in your head. Just saying it like this, writing it down on paper, saying it aloud in your head, is a good way to detect if we made any weird mistake. But we did it, folks. That's the 3-step problem solving strategy. Any last questions or thoughts on, really, we didn't do too much extra, but any questions on thoughts on this problem here? Okay, well, the last problems that we're going to be doing these notes is really just extra practice with these type of problems. There's a pretty good amount of variety here. Some of the problems, the next couple examples, go a little bit fast. They're building in complexity, so some of them take a little bit more thinking time. Really what we're focusing on is unit analysis, and if we get stumped on any of the problems, we're not sure if we're supposed to be multiplying or dividing, we'll think about this process as well as we go through the next problems. So let's forge ahead. On the next bit, I have this screenshot that I took just straight out of the textbook, and this is going to guide us from converting problems like we see down below in mostly nothing but words into the typical mathematical operations that will form the conversion factors like we worked with in the last problem that will tell us what our answer should look like. Should we be dividing things? Should we be multiplying things out? And so this is the major box that's going to help us, not for every single situation, but it's a great guiding principle of what should we do when we see the word, say, per, for example. The word per is often going to indicate division. The word of comes up. We usually think of that in terms of a multiplication word. Squaring something means some unit got raised to the second power. So for example, feet times feet would be read as feet squared. This will come up a lot if we're dealing with, for example, areas. We'll have the square of that unit. If we say cube something or cubic in any kind of context, like cubic feet, cubic inches, we would mean feet times feet times feet. It's kind of annoying to write that down. So the convention is write feet once as ft and put in a power 3 to say you're raising it to the third power. So that's what we mean by cubes. And that'll get involved when we're dealing with volumes. So if we have a volume problem, then we should expect a unit in terms of, say, cubic feet or feet cubed, cubic yards, and so on. Well, any questions, folks, with a quick table here? Okay, so other things we'll worry about and watch out for is if we have mixed units coming up in the problem, we cannot add, subtract numbers with different units. But if we do the right conversion of units, we can make them compatible. So here's our first example to get started, and one just overall big remark about essentially any problem that we do in class. We won't say this every single time in the instructions, but if we're dealing with money and there's nothing to say to round to the nearest dollar or anything along those lines, the assumption will always be that we're going to round to the nearest cent. And that's the same assumption for the MyLab homework exercises as well. So here's our first problem to start us off. And again, a lot of people have really great number sense. They know exactly what to do when they look at this kind of problem, but we're just focusing on the strategy of the unit analysis side. So we're going to take our time with every single one of these problems, dissect them to show what that process looks like. If you're doing this as an exam question and you pulled out a calculator, I forgot to load a calculator. Let me do that really quick here. If you're doing this in an exam situation, you pulled out a calculator and just computed the answer, put it down on paper, I would give you full credit for the right answer. But if there is anything wrong with that answer, then I may not be able to award partial credit unless there's some steps shown. So particularly for quizzes and exams, try to show as many steps as makes sense to you. You don't have to show tons and tons of steps. But the more you show is essentially just insurance. If you make the smallest mistake, I can use what you have here in your work to award partial credit. So let's give this one a try. It says It says to calculate the cost of 2.5 pounds of apples at $1.89 per pound. So one thing that jumps out at me is the per comes up in this information, which indicates division, as the keyword is saying here. We could take this whole piece of information and convert it into what's really a rate. It's a rate of $1.89. Per just means division, so we can just form a fraction right away. You could just put LB for pound. If you want to be specific, you can say 1 pound. Really, it's just a stylistic choice if you put the 1 in or not. So we have, I should make that just rate singular. We have the rate of $1.89 per 1 pound. And this would be equal to 1. It's now a conversion factor. Altogether, you could say 1 pound of apples, but I'll just leave it as 1 pound, leaving the fact that we're talking about apples just in the context. So now when we're thinking about this problem, it says calculate the cost. So that tells us, if we're thinking about the problem-solving strategy, the thing that we're trying to come up with is just a dollar amount. So in order to solve this problem, the conversion factor we use should have the dollar amount in the numerator. Really, there's 2 conversion factors here. You could flip that fraction around and it's just as good to use. But if we want dollar as the overall result, then that's what should be in the numerator. So from here, this part of the problem says dollars must be the answer. So this is now the full solution to our problem. Take the 2.5 pounds. I'll abbreviate that to LBS like we did on the other exercise. This we want to convert into a cost. They gave us a rate of $1.89 per 1 pound. So we just take that factor. The fact that we said it's equal to 1 is just to tell us we're allowed to take 2.5 pounds, multiply by $1.89, over 1. So we're not changing the numerical value of the 2.5 pounds. We're just changing the unit, and I forgot to put down over 1 pound. We're just changing the unit altogether. So essentially, now that we're at this stage, this is what we were doing with a lot of our problems way up here. We go back through memory lane of dealing with fractions. Say, let's look at a better one. That one should be decent. If we have one quantity here, one quantity in the denominator, just like how we had really a 7 times 3 here, a 7 times 1 here, can cancel from a denominator up into a numerator. That same kind of work applies if it's a unit as well. If you say 1 pound, pounds will cancel from a denominator into a numerator. Leaves just $1.89, so our unit is now in dollars. And really the last thing to do is just take the 2.5 times the 1.89. And again, many of you probably already knew that really all you had to do is multiply those 2 numbers together. We're just, again, focusing on the unit analysis side of this as we warm up through these problems. So here's the whole punchline to this one. 2.5 times 1.89 comes out as, in dollars, 4.725. But we know from experience, if you're buying 2.5 pounds of apples at, say, Albertsons, they're never going to charge you 4.725. This has to round to the nearest cent. And that'd be the answer that would be expected in my lab. If this was a quiz and you left it there, I might write a comment on there, but I'm not super picky on rounding if it's a quiz or a higher stakes exam. But my lab is, so we're going to be very careful with rounding just to help out with the homework primarily. Well, based on our practice with rounding, because we have the idea we want to round to the nearest cent, we look at the hundredths place value. To the right of it, it's 5 or bigger. It's 5 exactly, so we round up. The 2 goes up to a 3, and we would be charged $4.73. And that's our answer. That would be the cost altogether. Some supermarkets might round to the nearest nickel because of the penny shortage, but we're going to ignore that kind of information for these problems and just round to the nearest cent. But any questions at all, folks, getting through this one? Okay, well, that's what the theme is for a lot of these problems that we're going to be solving. And again, a lot of these go pretty fast. But we're going to see some just in these notes where we need to take some thinking time, see how everything comes together, and really focus hard on the unit analysis side of this. So think of example 7 as the warm-up, same with example 8, and we're building to something towards the end of these notes and going into the very next unit. So this next one is really short as well in terms of the context. It asks, or it says, if a person is paid $1,158 for 40 hours of work, what is the hourly wage? Well, on this one, asking for the hourly wage, the hourly wage is a rate, and that rate should be dollars per hour. So that's what we're expecting when we say hours per hourly wage altogether. They're not asking for the weekly wage, monthly wage, or anything like that. So that tells us the thing that we're trying to solve on this one, it's not going to have a singular unit like this one, dollars. We're combining two units altogether. This time the answer is the rate itself. So because we know we're expecting dollars per hour, we can just take the dollar amount, 1158.00. So that's the dollars portion for the numerator. When it says for 40 hours of work, notice they didn't say for anywhere here. So that's one of the things that's kind of inconvenient about these sort of tables in the English language. There's like a million ways to say one concept, and this table can't capture everything. So in our particular context, when they're saying for, we're really thinking in terms of dollars per hour. You could say amount of dollars for 1 hour, and it's the same exact information. So this just is telling us to divide by the 40 hours. So take 40 hours in the denominator. And that's what we have to compute. When it says hourly wage, we mean per exactly 1 hour, but now all we have to do is divide by 40 and we get exactly per 1 hour and our overall answer. And once again, if you're feeling like, man, I could have solved this in 5 seconds, I agree with you. This is a comment that I kind of repeated quite a bit. We're just practicing to see how these go so that we can see what's happening with the larger problems. But any questions at all, folks, on how we put that fraction together? Okay, well, really, once we know how the fraction combines, all we now need to do is just run it through the calculator. Again, if you have a calculator with you right now, that's probably going to be a good idea to have one available ready to go at the start of every class, because now you're just practicing what would you do next if this was a problem on exam 1. We're going to be practicing the calculator pretty heavily just about every single class period. If anything goes weird in your calculator, if you have any questions about any of the keystrokes you need to use, anything along those lines, don't hesitate to ask about calculator issues as well as we're going through these notes. So let's take 1158, divide by 40. We get 28.95. The unit, however, is going to be $28. When we divide by 40, it still leaves the hours unit in the denominator. We didn't actually cancel a unit like we did in example 7, pounds with pounds. Unit hours is still there. It has nothing to cancel with. It's just now per the 1 hour. Or you can just say hour for short on this one. If you left it like that, that's a great way to express the answer. And it's just as equally valid to rewrite it as $28 per hour. So I'll leave it up to you how you like to format it. The hourly wage just implied you're going to say how much money per the singular hour. So it had to be a 1 in the denominator, formatted in this way. Well, we did it, folks. That's the conclusion on the unit analysis side of this one. Here, we were going for a rate. On the prior example, we had to use a rate to just get to 1 unit, just dollars, nothing in a denominator for any other unit. Any questions with either versions of those examples? Okay, well, we're going to start building towards more interesting problems as we go. So here's the next one, example number 9. I think it deserved its own page. Let's drop it down here. So here's the new scenario. Imagine you live in a home with a basement. This particular basement is 20 feet long, 15 feet wide, 10 feet high. So 2 questions it has. First question is, what is the floor area to this basement? And this is a pretty fast computation as well. Area is just length times width. So if they give us, it's 20 feet long, the width is 15 feet wide, we can just throw that all together and get an answer out. But just for the sake of a problem-solving strategy, let's do a little bit more with this one just to see how this information combines. So one strategy with problem solving of this type is if you can draw a picture, it's usually a pretty good idea. So here's my picture to match this situation for this particular basement. Let's see here, 20 feet long, 15 feet wide. I think the best way to draw that is a couple skinny rectangles like this. Let me just draw it in segments. So the height of that rectangle is going to be the 10 feet high portion. Now draw the same exact size, but put it off and over to the side, kind of like this. Try to make the length about the same to the best of your ability. And now just kind of connect these corners. I'm not an artist, so this is kind of tricky for me. I usually practice these things before class, just so I make sure I don't spend too much time trying to draw them out. Okay, so here's about how it would look. You could, if you want to, be really picky on which parts you can see, which parts you wouldn't be able to see from this point of view. So dashed line means you can't see that part of the wall here or that part of the wall here based on our line of sight. And that's the basement. We're imagining that somehow you can see through it with no floor above it. We have that it's, let's see, 20 feet long. This looks a little bit longer, so let's call this 20 feet. 15 feet wide, I'll call this the width at 15 feet. It's 10 feet high, so the height is 10 feet going this way. Now we just plug in the information. Area is length times width. There's lots of different areas though. When it says, however, specifically floor area, we're talking about this particular area. We don't mean the area of any one of the walls, for example, which would have different areas going this way versus going this way. So anything you can kind of do to visualize the problem, maybe so you have a really good imagination, you can just visualize this kind of structure in your mind. That'd be amazing and very useful. That helps us decide what's really the L, what's really the W in the problem. So for this one, we take area, whatever the length is for the problem, throw it in. So 20 feet going here. It did help us with instructions saying that that's 20 feet long, and we know we're doing the floor area. Multiply by the width. Width goes this way, 15 feet. Now we just put those two quantities together in the calculator, and we'll have an answer out. So 20 feet times 15 feet. I do not know that off the top of my head. Let me throw that in. 20 by 15 is exactly 300. But also, just like we saw from the last screenshot out of the textbook, since we're dealing with feet times feet, altogether, we just abbreviate that to feet squared, which we're expecting because we're computing an area this time, not a length, so it will be 300 feet squared. So if you had to, say, paint the basement floor, cover it in some weird epoxy, anything along those lines, you'll have a good idea of just how much you're going to have to buy at Home Depot or something along those lines. So that's the area of the basement floor. Any questions at all, folks, putting all that information together? Okay, just want to kind of reset my drawing. And here's the next interesting part of the problem. Now we have some drama entering into this. Basements are kind of vulnerable. If it hasn't been recently dry locked, it can have all sorts of issues, especially when we have long periods of rain here in Idaho Falls or Pocatello. It goes on to say next, if the basement floods to a height of 3 feet, that sounds catastrophic. I'm not sure if that's the height of, say, an electrical socket, but let's just say that happens. We want to know what is the volume of water in the basement. If you work for some kind of emergency cleanup crew, then that's something they're going to have to calculate to determine the estimate for trying to save this basement. So we want to know how much water is now in this basement. So we go up a dimension. Volume is going to be length times width times height. We've already done the length times width, so really we're just taking the new element for height here. And it's easy to kind of lose our way on this one. This problem is sometimes trickier than it looks. So watch out for these kind of problems in, say, the MyLab homework system. Anyone see what the height here should be? Yeah, good call, Cooper. It should be exactly 3 feet. The reason this problem is kind of dangerous is it's really tempting that now that I've drawn a figure right here to throw 10 feet into the problem. But that means the entire basement's an aquarium, right? That's not what happened. That would be like really, really bad floodwaters if that ever occurred. All we're doing this time is saying the height is 3 feet of water. We're just trying to find not the volume of the basement, the volume of the water that has to be removed some way, somehow, or maybe just left to slowly drain over time. So height in this problem is 3 feet. And now we can plug information just like we did before. So volume is going to be the length of 20 feet times the width of 15 feet times the height for this context of 3 feet high. We already know what 20 times 15 is. That came out as 300. So we can take a shortcut right here and just say, first two things multiplied, 20 by 15 is 300. Then times that 3 right there. The unit is now feet times feet times feet. So we're dealing with a volume for feet cubed, much like how we are dealing with feet squared for area, but just higher dimensionality this time. Now take 300 times 3. I didn't quite do it. Let me try again. Take 300 times 3 to get altogether 900 cubic feet of water is now sitting in the basement. So that's a really big job at that point. That's kind of unfortunate. Probably that's going to take a lot to clean up, a lot of work to get out of there. But now we've got an answer at least. Well, we did it, folks. This is us building a little bit more on unit analysis on example 9, but also just focusing on different kinds of units is the big takeaway, dealing with an area formula or a volume formula. If this was a real exam question, then it's easy to get frazzled on an exam and just kind of forget formulas sometimes. For these kinds of formulas, I'd probably have it printed out in the exam. Something like use the fact area as length times width, use the fact volume as length times width times height, that kind of thing. So you're not going to be tested on extraneous formulas. It'll be stuff that you're familiar with. And if it's just a random formula like areas and volumes, I'll have it baked into the exam. But any last questions at all, folks? Getting through example 9? Okay, and just for fun, because we've done this already, if you're curious on what happened on example 6, when it was 25 cubic feet of water, it weighed 1,560 pounds. Let's see what this one is going to come out as. It's this time 900 cubic feet of water, so 900 times. The punchline to this problem, example 6, to find the weight of water is multiplied by 62.4. So reusing that same idea, if you go into, say, disaster cleanup and restoration for people's homes, you now know that you're going to be dealing with 56,160 pounds of water. So that's going to take a lot of efforts to pump out of the basement. Probably not going to be hauled down trucks, probably just pumped out and dumped into the gutter or something like that. But now you have a pretty good idea of what to charge people based off the size of this job. So it's good to kind of imagine some kind of context behind what's going on to see the purpose of the problem. And for the next one, we're just going to keep on building off these kind of ideas. So here's our next challenge problem to take a look into. I think we can potentially fit this here so the overall end notes don't get too big, too many pages. So we're still talking about tanks, and we're now in the similar vein we were just discussing, pumping water. We're told that for this context, a pump fills a tank at a rate of 3.5 gallons per minute. We want to know how many hours will it take for this pump to fill a 420-gallon tank. So that's really pretty specific information. We know the fill rate of this is 3.5 gallons per minute. One thing that's kind of concerning about this problem is we have per minute given for the supplied rate, but the question is how many hours? That means we have a unit mismatch. And that's okay. We can correct this. This sometimes is going to happen in the homework as well. So that's its purpose here in the lecture notes as well. So the answer to this question, thinking about our problem-solving strategy, is we're just trying to come up with an answer in hours. So the answer is just going to be in hours only. We have a tank that needs to be filled, 420 gallons. So that's one element of the problem. Let's go with green on that. And another thing that we have going on is the pump's working hard. We have a rate given, 3.5 gallons per the minute. So per there, once again, tells us we're dividing something. Let's rewrite this out as rate is 3.5. I'll abbreviate gallons to just GAL for short. 3.5 gallons per, I'll use MIN to abbreviate minute. So that's our rate given. It's incompatible with what we're trying to do since we want an answer that's going to be hours, but we can still work with this. So let's go over here. We want to answer in hours. We can just write down an equation that 1 hour equals 60 minutes. Once we have an equation like that, it implies, just like we saw in example 6, 2 conversion factors. This equality here means you could divide both sides by 60 minutes. You would then have 1 hour over 60 minutes equals 1. So that's one equation we get. Or you could just as well divide both sides by 1 hour. Then you would have 1 equals 60 minutes, divide by 1 hour. So now we have two conversion factors to compete with. But if you looked ahead and knew that the answer should be in hours, it means this is the conversion factor that we need to use, the one that has hours in the numerator. Also, if you're looking ahead at minutes being in the denominator, then that kind of helps out as well. Let me double check my thinking here. Hang on, that's not quite right. Yeah, that seemed right to me because I want answer in hours. That part's still true. But actually, this conversion factor isn't going to do it for us. A little bit more going on with this problem than I anticipated. But let me first show what would go wrong. What would happen if you took this and multiplied it here? I'm going to erase this in a minute, but you would get 1 hour over 60 minutes, and it would look like that. Please don't write that down in your notebook. That doesn't look like the right way to go, because now you're going to have minutes times minutes. That's not too different than feet times feet, but minutes squared has no meaning whatsoever in this problem. So that tells us we're not on the right track with that as a conversion factor. We should use this one right here, 60 minutes per the 1 hour. So if we take that factor, let's go times 60 minutes per 1 hour, then at least converting this rate will make sense. We can cancel minutes to minutes. Now we have 3.5 gallons per the 1 hour, which is what we're expecting. So cancellation going here, cancellation going here would do the job. And so expecting the answer in hours is a little bit trickier in this problem. There's a little bit more going on. But the unit analysis side of this, where the minutes and minutes have to cancel, at least can help us prevent going too far into a mistake. But does that make sense to folks on why we had to select that conversion factor here? Okay, so we have that multiplying, we're converting 30.5 gallons per 1 minute into gallons per hour. But what this side just implies is we're just going to multiply across the numerators, keep gallons per hour. So 3.5 times 60. We're going to get 200 in the numerator. So now that's 210. 210 gallons per 1 hour. And I'm ran out of space, so I'm just going to use HR short for the 1 hour. I guess I did that already over here too. So a lot of fighting just to fix the flow rate. 3.5 gallons per minute is now 210 gallons per 1 hour. But we still haven't answered the question. The answer is going to be in hours. We have a rate here, and we never have used the 410 gallon tank whatsoever. And one good problem solving principle is if there's an element of a question like this that we just never even touched, there's a good chance that we're probably not on the right track of it. These kind of textbook style questions usually are only going to give you the information that you need, nothing extraneous. So we converted the gallons per minute. Now we're going back to the 420 gallon tank. And we have to do something with this. We have a flow rate, so we just have to decide, should we multiply this or divide this? Any volunteers to say how we should use that rate? Is that a multiplication or a division? kind of a tricky question on this one, right? So to kind of decide which one it should be, here's one way to think about it. Nicholas says multiplication of the 210 by 2. Yeah, I think that should pretty much do that. If you do that multiplication that kind of way, you're going to get the result of 2 hours, and that answers the question. It'll take 2 hours by multiplying this entire rate by, say, 2 over 2 to get to that 420. So yeah, that's a great way to think about this one. So that one would take us right to the answer there, as Nicholas mentioned in the chat. And yet another way to think about this one is the reason we can't take the 210 here and multiply it over is because you'd be taking 210 gallons per the 1 hour, and that's the same kind of issue as we had before. The unit analysis tells us you can't take gallons times gallons. We've got gallons squared now. It's hard to say what that would even mean in this context, especially when we're expecting an answer in hours. So instead, we could just divide this. You could just say multiplication doesn't work. Divide by 210 gallons per the 1 hour. Our work with fractions says this just converts over to multiply. We flip the fraction over here, and you get all together 420 gallons multiplied by the reciprocal of this flow rate now, 1 hour, over 210 gallons. At this stage, our problem is essentially over. Gallons to gallons, they're just going to cancel out immediately. 210 divides into 420 exactly twice, and the unit left over is in fact hours, which we're expecting. So we would get 2 hours solving this problem. So in other words, once you have the flow rate converted, there's really two great approaches. We had to divide by it, which meant multiply by the reciprocal, or the other strategy, let me write this down below here as another great method, is take our rate, which came out as 210 gallons per 1 hour. And as Nicholas mentions, if you multiply the 210 by 2, it gets to the amount in the tank. It's just convenient. The numbers are nice, right? Multiply by 2, we're at 420. Our work with fractions, we have to really multiply by 1, so we'd have to multiply by 2 down below. This would give us 420 gallons per 2 hours. And then we just have to make sure we indicate the answer is just the 2 hours. So either way we go at it, let me put a box on this one because the work kind of spilled over everywhere. The answer for this is going to be 2 hours. So now we know if we're dealing with 420 gallons, maybe it's in a basement, for example, and we're using this pump to empty it at 3.5 gallons per minute, it'll get the job done in 2 hours. So 900 cubic feet is going to be more concerning. That's going to take a lot of time to get that done. But any last questions or thoughts at all, folks? Running through example 10.
Yeah, I have a question.
Yeah.
Can you please go over again why you decided to pick the 1 equals 60 minutes over 1 hour over the vice versa?
Yeah, absolutely. That's one of the things that confused me myself when I was first looking into this problem. So we had an original rate equals, we are down here, 3.5 gallons per the 1 minute. And I was looking ahead thinking, well, I know my answer's got to be in hours. We got there. The answer is here, the 2 hours. But that doesn't necessarily mean you always use the one with hours in the numerator. It just depends on the problem. The fact that we actually have to divide right here is what caused that kind of conflict. But here's what another principle that ultimately gave us the decision. If we take the numerator out, and multiply by, say, 1 hour over 60 minutes, well, it's really one. So we didn't change the rate, we're just changing the unit. But here's what happens with the unit. We would get 3.5 gallons times hours. Let's try it this way. Gallons times hours divided by 1 times 60 would give us 60. It's now minutes times minutes, so minutes squared. That deserves a question mark because there's nothing wrong with the numbers we have. They're right, but the units don't really match the problem any longer. The units kind of turn into a mess. So that's why we kind of reversed engineered this and we said, well, let's abandon that, uncircle it, circle this one instead. Look at the rate again. Rate equals 3.5 gallons per minute. We just want to know gallons per hours. So if we instead multiply this way, 60 minutes times divided by 1 hour, then we're suddenly on the right track with this one. The reason is cancellations work from numerator to denominator and even going across fractions in this way, like we did with our fraction warm-up at the top of the notes. So those minutes would cancel out just fine. There'd be no issues there. We'd have surviving units, gallons per hour. We can say per hour because hours are being divided. So that's where we got the 3.5 times 60, 210 gallons. Divide by, minutes are now gone, so we just take 1 times 1 for 1, and hour survives. This means we're on the right track. We just took something that was in gallons per minute. Now we have gallons per hour. We don't have a gigantic mess of units like this right here. That's really hard to even think about what's being conveyed. And so that's why it had to be this denominator one. So the really, really short answer is we need to pick the one that causes a cancellation of units in this kind of way, and that will send us on the right track. So it had to be that second fraction. Does that make sense with that second look at this one?
Yes, that was very helpful. Thank you.
Yeah, absolutely. And again, these could be pretty tricky. That stumped me at first, thinking the first one looked right. Just depends on what you're ultimately doing in this problem. It was ultimately a division problem. So guessing right at this stage which fraction wasn't quite enough. This is probably the better way to think about it. Which units will really actually cancel? Other questions at the moment with this problem or others? Okay, let's see what else we've got going on these notes. We're very near the end, but there's still plenty of interesting kind of questions to answer. Example 11, it's kind of like the flow rate problem, but this time we're looking at the mortality rate. So a little bit morbid, but it's important information as well. We'll look a little bit more in conversions, feet to inches, weeks to seconds. But let's take our time with this one right here. So again, these problems can get kind of tricky. It's easy to lose our way and accidentally write down weird fractions with units that don't make sense, accidentally multiply when we're supposed to divide or vice versa. So a really good guiding principle with a lot of these is still all the way back up to here, the problem-solving strategy along with unit analysis. So let's think about that as we read through this question. It tells us in a population of 250 million, so around the size of the population of USA. USA is a good amount bigger, but this one is a decently big country as well. We're told for this country, there's an average of 500,000 deaths per year, so 500,000 per year. We want to ask, what is the mortality rate per 100,000 people? Mortality rates are pretty picky. They usually normalize them to the mortality rate per the 100,000. So that's why this question seems awfully specific. So we know there's that many deaths per year. We're trying to standardize this mortality rate to 100,000 people so that we can compare across different countries. Compare this country to USA, for example, to see which has a higher or lower mortality rate. So this whole problem, in step one, understanding the problem, we're trying to determine what are we solving for? What is the unknown? Usually the question mark is a good place to go for determining the unknown. The unknown is the mortality rate per 100,000. Let me focus just on that wordage right there. Mortality rate is going to be deaths per year. So we want to know the mortality rate per 100,000 people. So the unknown is going to be deaths per year per 100,000 people. We can find that value, our work is completely done. So we know what the unknown is. Now we have to somehow use the given information. This needs to be used somehow, some way. We have a country with a population of 250 million. The mortality rate, or death rate for short, is 500,000 people per year. So we're now on the solve the problem side of this. We need to compute something to try to get at the number of deaths per 100,000. So notice the per 100,000 people indicates that when we go to write out our computation, we need to have people in our denominator. So that's going to form the unit for our particular denominator. And this country that we're working with, there are 250 million people altogether. So that information must go down into the denominator. So let's take 250 million. We could write it with the unit of million, but I think it's more convenient to just expand this out. 2, if it's in millions, we'll go, hang on, let me try again. 250 million, so go 250 first. If it's in millions, we now need 6 more zeros. So there's our 250 million people. So we're thinking about this side right here. We don't have the right number, but we're using the given information, 250 million. So that's why we threw that into the denominator. When it says per 100,000, that's the division and why it's in the denominator. So for this particular country, it's averaging 500,000 deaths per year. So that's our unknown number of deaths per year. We can throw this into the numerator, 500,000 deaths per year. And notice that's really a pretty complicated numerator. The numerator itself could be re-expressed as 500,000 deaths over 1 year. You could just rewrite it in that format if you really wanted to. I wrote it like this, just saying deaths per year, because I don't want to have a fraction in the numerator of the overall fraction. It starts to get really easy to get mixed up and lose our way. I want to focus primarily on the 500,000 and the 250 million. So I left it just in this format rather than rewriting it as a fraction. So all I've done so far is take the mortality rate, 500,000 deaths per year, divide by the population, 250 million people, and that's where we're going to start with. We want to know the mortality rate per 100,000 people. So if we can get 100,000 into the denominator, our work is completely done. But again, this one's tricky just to know what we're trying to solve for in the very first place, get the units just right. Any questions at all, folks? Getting information down to just the stage on paper? Okay, well, here's one strategy next. If we're trying to get deaths per year per 100,000 people, one thing you could do is just take your 500,000, divide it into 250 million. There's multiple strategies for this, but I'd say that's a decent one to start off. Simplify the fraction, in other words. So kind of again, the stuff that we did at the top of the notes, just that the numbers are a little bit bigger, a little bit more messier, but also we're using the calculator to form a lot of these computations. So take 250, 1, 2, 3, 4, 5, 6, careful with those zeros, divide by 500,000, so 500,000, and we'll get exactly 500 in the denominator. So we'll have one death per year over 500 people. So 500 goes into itself once, so one there. Through the calculator, we found not 500, but 500,000 goes into 250 million 500 times. So the fraction is now reduced. We're still not where we want to be because we want per 100,000, but we're getting there. We're chipping away at it. So next thought is, if we're trying to get to that 100,000, the denominator has to change, which means the numerator is going to have to change as well. We have to multiply by something over something. So here's one way to think about this. I need to know, what do I multiply 500 by in order to get 100,000? So you can take that whole piece of information and just say 500 times something, let's just call it X, needs to come out as 100,000. So that's going to tell us X is the question mark right here, going down below and up above all at the same time. Once we get that, we'll be at a mortality rate per 100,000 people altogether. But here, this just tells us to solve this, you just divide by 500. So take 100,000, divide by 500. It tells us that this should just be 200. So if we divide by 200, that's not quite right. You can't just divide the denominator by 200. You've changed the numerical quantity of the fraction, but also multiply by 200. We're just multiplying by the fancy number one, just like when we were forming least common denominators, that kind of stuff, or canceling with conversion factors. Multiply, divide by that quantity, and here's what we will get. Just to verify, we know when we multiply fractions, we multiply across the denominator. So as a double check, 500 times 200, yeah, it really is 100,000. So we get 100,000 people. That fraction bar doesn't have to get that crazy. Let's go like that. 100,000 people. So that's multiplying across the denominator, keeping the unit. Multiply across the numerator, keeping the unit. 1 times 200 would be 200. Unit will pluralize now and call it deaths per year. So now we know the number of deaths per year. We knew it was 500,000 deaths per year, but we want to know that rate per 100,000 people in this particular country. So now this is the factor you can compare this with against other countries. The mortality rate per 100,000 people is 200 deaths per year. That one is kind of a weird one, right? It feels like we had to jump through multiple different kind of hoops just to get to the right spot where we needed to be. Any last questions or comments with this one, or different strategies that you might have taken? Okay, well, this is a sort of problem that we'll be returning to on the last part of the semester, it turns out. We're going to look at population growth models, and as far as population growth goes, mortality rate is part of the picture. You have to know how many members you're adding to a population, how many members you're tragically subtracting from that population. And so mortality rates will make a comeback towards the last part of the semester. So this problem is tricky once again because it's hard to know what we're really solving for, but writing it down on paper, what you're going for, primes the mind on how to put the information together. And then it was just a matter of reduce the fraction, then try to fit the fraction so the denominator comes out exactly the way we needed it. So this is the end answer to this one. And in my opinion, a pretty tricky one getting to that spot. For the next problems, we'll take a look into example 12. We're going to do some conversions, feet to inches. Part B is going to be interesting because our semester here is 16 weeks. So now you'll be able to answer the question of how long is our semester in seconds only? That seems like it's going to be a pretty large number. And then we'll end with some problems dealing with geometry, some unit conversions. But really, I would say from this point on, examples 12, 13, and the final example 14, really this is just for the sake of extra practice. We didn't quite solve this one completely like the syllabus indicated this week, but again, we're going to take our time with these and not try to rush through them. But if you want to get an early start on the homework in Unit 2A, you should be in a good place to solve every one of these after solving the last question that we just got through. If you get stuck on any one of them, don't hesitate to ask. I'll be very happy to help out. You can send questions on the weekend even. I answer my email typically in the morning, so right around 8:30 a.m., sometimes 7 a.m., depending on when I get up. But don't hesitate to write if you get stuck on any one of these. And if you have questions about these problems, say on when we come back on Monday, that'd be a great one to start off class with as well. So we'll come back on a little bit more fresh on our Monday. We'll talk a little bit more about exam one and testing centers, that kind of thing. I'll send you some information. But any last questions or thoughts at all, folks, before we call tonight, the end of week one? Okay, well, have a great night, folks. We'll be back to this chipping away at the course on week two, just 15 more weeks to go. Take care.
Thank you.